We start off by examining the urgent need for energy storage to support the rise of renewable energy. On one hand, we have an increase in variable renewables, which demands more flexible supply sources. On the other hand, our traditional power generation is becoming less economical. BESS meets these challenges by discharging energy for the peak demand situations and helps stabilize the variable output from renewables, ensuring smooth grid operation. It also plays a crucial role in delivering ancillary services for grid management. The challenges created by the variable nature of wind and solar power are well known. This is especially the case in energy systems with high share of electricity generation from renewables. On days with high share of renewables in generation, conventional power plants are ramped down. Fluctuations in wind and solar generation caused by windstorms or cloud cover can lead to significant swings in power production. Such volatility can have a substantial impact to the grid, as the renewables generation levels can drop or surge dramatically in minutes or even seconds. Such unpredictability requests for a flexible generation fleet. BESS stands out as a solution for these scenarios, offering the ability to respond rapidly. And so if we talk about advanced technologies, then I really think it's important to see where we came from in the first place. And this timeline provides a great representation of our journey so far. The path to today's advanced high-tech BESS has been long and filled with innovations. From the early days of flywheels and fuel cells to various types of batteries and pumped hydro, energy storage has evolved dramatically. It's fascinating to think that pumped hydro storage remains one of our best assets for large-scale energy storage, particularly in regions with suitable terrain and geography. If we focus on BESS, their usage in power systems evolved significantly. Some of the first BESS emerged as pilot projects in microgrids. Today, utility-scale BESS are becoming standard assets of power systems, mainly of lithium-ion type. Other technologies are advancing as well. Well, for those of you who are still asking a question, is there really a need for energy storage at a utility level? We say, and we already see, that the answer is absolutely yes. In the future, BESS is going to play a crucial role for both utilities and consumers. Now let's take a moment to examine some growth charts that show the remarkable surge in BESS. There is definitely a booming trend, with some extreme estimates projecting around 4 terawatts of installed battery capacity by 2050. The values are so high because this estimate is based on the scenario that complies with the 1.5-degree climate target from Paris Agreement. If we focus at the utility-scale BESS, they are already dominating new annual capacity additions, and it is expected to grow at a rate of around 30% per year until 2030. This makes it the fastest-growing segment within the battery energy storage market. Obviously, as we see in the chart, major economies are going to lead this growth, with China at the forefront, followed by the US, Germany, and Australia. From these charts, it is clear that while BESS may not be able to solely provide a solution in enabling the energy transition, they certainly stand as one of the primary technologies driving this transformation. Moreover, BESS manufacturers are evolving their products from simply producing batteries to providing comprehensive solutions. What we see today is the availability of easy-to-install DC battery containers, but in the future we expect to see standardized AC solutions as a norm. So in this slide, what I really want to talk about are the multiple benefits around the battery energy storage systems. And as I mentioned earlier, by being able to manage the swings of intermittent resources, we're actually going to be able to integrate more of the renewables into the grid, which is everyone's goal. We also can't reduce any of the reliability or resiliency for the consumers by doing this, so we must ensure that everything that we do is not only doing the right thing from a climate aspect, from a price aspect, but also from a resiliency and reliability aspect. And one of the other words that you're going to hear a lot nowadays is flexibility. And flexibility is going to be truly the key for how well we're going to be able to operate and maintain the grid of the future. And BESS can give us exactly that, flexibility. BESS is one of the most flexible types of assets that the utility can push forward in the future. Therefore, we can say that the strongest benefit of BESS is enablement of significant renewable penetration into the power system. When it comes to advantages of BESS in comparison to conventional T&D solutions, these are numerous. Conventional solutions often follow a one-size-fits-all approach and can become obsolete if demand doesn't develop as expected. On the other hand, BESS offers high modularity with a right-size capacity for the grid, compared to the block sizes of traditional solutions. Due to its versatility, its usage can be adapted to the actual system needs. It can also maximally exploit existing grid capacity as a non-wire alternative. BESS projects can be deployed at a fast pace, as we have already seen in the past. When it comes to response rates of BESS, here we can count on a sub-second response time, which makes it a superb choice, especially for frequency regulation. Fast response also means that less megawatts are needed in the system to balance the grid. BESS is also an environmentally friendly choice. BESS systems offer a wide range of functionalities, of which we already mentioned a few. Now let's explore some typical use cases for BESS applications. First, there's peak shaving. This involves storing excess energy when demand is low and releasing it during high demand periods, effectively leveling out the peaks. Next is energy shifting, or arbitrage. Here, a BESS discharges when electricity prices are high and charges when they are low. Essentially, it is capitalizing on price fluctuations for economic gains. It's all about playing the market right. A crucial function of BESS is frequency regulation and grid balancing. And here it's all about maintaining continuous balance between power generation and load, compensating for the fluctuations. For resilience, BESS is key. It can keep an islanded grid, like a microgrid, powered even if the main grid goes down. Here especially a grid-forming capability of BESS becomes important. During outages, BESS proves invaluable by supporting critical loads, thus ensuring continuity and providing much-needed backup. We already said that BESS is a key enabler for increasing the share of renewables of the system. BESS evens out the ups and downs of wind and solar, increasing system flexibility. BESS can serve as an operating reserve. These are engaged to restore the generation and load balance in the event of a contingency, such as a sudden, unexpected loss of a generator. Lastly, utility-scale BESS can delay the need for expensive transmission grid upgrades, by giving us a smarter way to manage the grid. Recent development projects in the US have highlighted the growing significance of ancillary services in BESS usage. Analysis reveals that these services, particularly for frequency regulations, spinning reserves, arbitrage, and managing excess renewable generation, are becoming primary applications for BESS deployment. This trend is expected to persist for the foreseeable future, reflecting the critical role BESS play in maintaining grid stability and maximizing the integration of renewable energy sources. In Europe, a similar pattern emerges, with BESS currently being predominantly deployed for ancillary service purposes. However, there is an increasing focus on BESS solutions for longer-term energy supply. Incentives are being offered to facilitate the expansion of BESS applications beyond ancillary services, paving the way for wider utilization and improved grid flexibility. Let's very quickly look at some of the major components for a utility-scale BESS system. These are presented in the single-line diagram here. First, on the DC side, behind the inverter, there will be the complete battery system comprising battery racks and battery modules with cells connected in series. This battery system is connected to the inverter, where conversions from DC to AC takes place. Inverter transformers from all the arrays are then connected to a common medium voltage busbar. The voltage is further stepped up with a step-up transformer and connected at the interconnection point to a public grid. Alternatively, the connection point can also be the existing network transformer instead of a dedicated step-up transformer. An auxiliary supply transformer will be also part of the plant. This image depicts an aerial view of a 20 megawatt BESS project, showcasing the main components we just described. Battery containers housing battery racks. Each container is accompanied by inverters and an inverter transformers, all of which are connected to a large network transformer. Additionally, the plant will include a dedicated medium voltage switchgear system and an auxiliary transformer for supply. Other components such as BESS controller, communication, monitoring, and data recorder are also present. When considering the power ranges of BESS, depending on the segment, we observe sizes ranging from 100 kilowatts to 100 plus megawatt. At the utility scale, relative to the system size, we can say that the batteries of several dozens of megawatts are already considered as significant installations. In a large interconnected system, 100 plus megawatt would be seen as a big battery. Let's look at some of the significant BESS projects in service today. Looking back at 2017, we witnessed the integration of what was then referred to as the first big battery. The installation took place in South Australia under the project named Hornsdale. You may remember that this was a BESS installed at a record speed in just 100 days. Another project, also located in Australia, is the Victorian Big Battery with 300 megawatt and is currently regarded as one of the largest in the world. Just in recent months, what claims to be the largest online BESS in the world is located in California as part of a solar plus storage project with an approximate battery size of 750 megawatt. The total battery capacity is over 3,000 megawatt hours. However, a large number of BESS projects are either under constructions or have just been announced worldwide. It's just a matter of time before these BESS will no longer be considered the largest. In Germany, plans for a 1 gigawatt battery are already underway, and multi-gigawatt BESS are expected in the near future. Let's talk about BESS design criteria. When designing a BESS, several key factors must be carefully considered to ensure optimal performance and the length of life. First and foremost, we must define the use case. What purposes and functions will the BESS serve? Will it be for peak shaving, frequency regulation, or something else? This will directly provide us with required functionalities of the inverter, like whether we need islanding, black start, or reactive power capabilities. Next, we need to analyze the expected charging-discharging profile of the BESS. How does the battery's load profile align with its use case? This will help in coming up with the C rate of the battery system. High C rates are typically used for applications that require large amounts of power over a short period, like frequency regulation in the grid. Lower C rates are used for applications that require steady power over a longer period, like load shifting. Important question to ask is also where will be the point of interconnection for the BESS. This is a relevant aspect as it will determine any additional losses that should be considered. Finally, we consider the designed lifetime of the BESS, which tells us how long the BESS should operate effectively. Here, we look at the capacity degradation over time, considering effects of load profile and losses to the BESS lifetime. The idea is to ensure that we start with selecting the adequate initial BESS capacity. BESS can maximize their value to the grid and project developers by providing multiple system services. As some services are rarely called for instance black start, or used infrequently in a given hour, such as spinning reserves, designing a BESS to provide multiple services enables a higher overall battery utilization. This multi-use approach to BESS is known as value stacking. For example, a BESS project can help defer the need for new transmission project by meeting a portion of the peak demand with stored energy during a selected few hours in the year. When not meeting peak demand, the BESS can earn revenue by providing operating reserve services for the transmission system operator. Even though it sounds very nice to have the BESS utilized as much as possible, as we will see in this webinar, value stacking may not really be a choice for some utilities and system operators. Let's transition to this slide and explore the comprehensive support that Siemens PTI offers in the realm of battery energy storage systems. We provide a comprehensive portfolio of technical studies that will make your BESS planning and operation seamless. This includes everything from the feasibility aspects of planning and integrating the BESS to its design, grid impact, grid code compliance, commissioning, and operations. In the event of disturbances and component failures, PTI also has the expertise to help you investigate and identify causes. With our experience in major international projects, we have the capability to perform even the most technically complex studies. And our consulting is vendor agnostic, which means the advice from Siemens PTI is independent. There is no obligation to use Siemens software or products. When it comes to performing specific technical studies, Siemens PTI does more than just run standard tests. Through our studies, we cover a wide range of aspects. More importantly, we provide tailored advice to our clients regarding the necessary studies for their project. So depending on the circumstances and specifics of the project, we may recommend different approaches and types of studies. A lot of it will depend on the stage a project is in, but it may also depend on technical grid parameters around the project. For instance, if weak grid conditions are identified at the interconnection point, we may advise performing additional EMT analysis alongside RMS for dynamic and transient studies. Besides the standard steady-state, dynamic, and harmonic analysis to design or to verify the design and parameters of the components, we also conduct further studies, such as protection coordination to identify the correct protection device settings, voltage fluctuation to analyze the voltage dips in the system caused by energization of the plant components, short-circuit analysis to assess the impact of the BESS inverters on short-circuit currents within the system. Furthermore, we also perform evaluation of the black start procedures and system restoration procedures, lightning and switching over voltages to assess the installation coordination, current and voltage transformer dimensioning as well. We also perform other studies such as arc flash hazard, earthing studies to design grounding system, neutral grounding analysis, electromagnetic field studies to evaluate the impact on the surroundings, and many more. We will elaborate some further specifics of these studies as we progress throughout today's webinar. In conducting our studies, we use commercially available simulation tools such as our own world-renowned PSSE and SYNCAL, but also others such as DigSilent, PSCAD, ETAP, Neplan, SciMe, Aspen, MATLAB, and many more. With our extensive technical expertise, we are committed to delivering solutions that meet the highest standards of performance, safety, and reliability for any BESS projects. As we move to the next slide, we can state that both the energy system and BESS projects are becoming more and more complex. In such a dynamic environment, many fail to take a strategic approach to assessing project requirements and conducting adequate project studies. Instead, they carry out studies reactively and in an ad hoc way. However, this leads to many challenges: violations of project time constraints, poor design specification, non-compliance with grid codes, uncertainties in planning, and unknown grid impact. Siemens PTI helps clients safeguard their investment by taking a proactive approach to proper BESS planning and integration. Thank you for your attention to this point. Now, I would like to invite and hand over to my colleague Rafal, who will tell you more about grid boosters, which are a special BESS type used in high-voltage transmission systems. Rafal, the stage is yours.
Hi, my name is Rafał Lubiatowski. I am a senior consultant and a portfolio owner for protection and instrument transformers at Siemens PTI. I would like to give you some technical insights into BESS installations used as a grid booster in high-voltage transmission systems. The main aim of this kind of BESS application is to feed in power into the high-voltage transmission system within a very short period of time and stabilize it, for instance, in case of faults in the grid. We as PTI are involved in the largest grid booster project worldwide to be installed in Germany. In this project, we are responsible for performing different energy studies and checking the dynamic and transient performance of the grid booster. As the name suggests, the grid booster provides a rapid response triggered on demand by the transmission system operator. We could compare the principle of a grid booster to a conventional turbocharger in a combustion engine. It is there, but it steps in only if additional power is required. As you can see on the slide, a typical setup of a grid booster contains of a number of grid booster units. Each unit includes several battery racks, providing a DC voltage of up to 1.5 kV DC, and is connected through an inverter to the low voltage AC system. Using a 2 or 3 winding step-up transformer, a so-called grid booster transformer, the low voltage system is connected to the medium voltage level. One grid booster unit provides a power of approximately 10 megawatts. And the main limiting factor here is the maximum available power rating of the dry type power transformers. All grid booster units are running in parallel and feeding medium voltage bus configured as a single or double bus bar. The medium voltage level is determined based on the required power, insulation level of the equipment, and economical aspects. From the medium voltage level, the power is then transferred through a large step-up transformer that is connected to the high voltage grid. In Europe, this is typically the 400 kV voltage level. On the medium voltage level, we typically have some auxiliary transformers which are used to supply auxiliary loads like air conditioning, heating, lights, etc. Furthermore, depending on the star-point earthing method, the medium voltage system can be equipped with a star-point grounding transformer, which helps to detect and clear single phase-to-ground faults in the medium voltage system, such as cable or busbar faults. The total capacity of a grid booster is a few hundred megawatt hours. The required operation time is one of the biggest differences between the grid booster and a conventional BESS application. The grid booster is expected to provide a large amount of power over a relatively short time frame, for example for a few seconds, up to 1 hour, while other BESS applications may provide smaller amounts of power over a longer time frame. The next slide shows some typical challenges that play a role when developing, designing, and engineering of a grid booster. The first challenge is to provide results of electromagnetic fields study required for planned approval process by municipality. This study investigates the potential impact of electromagnetic fields on human health and is to be provided in a very early stage of the project. Early stage means that the calculations and simulations are often made based on some preliminary data. In this stage, it's important to have access to high-quality expertise and start on the basis of worst-case assumptions. These are key requirements to submit plant documentation that is plausible and of good quality. Another challenge is dealing with the maximum available short-circuit currents in the medium voltage system. Considering different operational scenarios, voltage levels of the high voltage system, and etc. During three-phase short-circuit currents, the medium voltage switchgear is exposed to short-circuit current flowing from the high voltage grid to the short-circuit current coming, of course, from the inverters itself. The sum of both short-circuit current contributions must not exceed the maximum permissible short-circuit withstand capability of the switchgear. When exceeding the limits, one can hardly limit the current coming from the inverters. But there could be some limitation achieved by increasing the impedance of the high voltage transformer. Unfortunately, by increasing the impedance, mainly the reactance of the transformer, the reactive power demand of the grid booster increases as well, so that sometimes a compromise needs to be made between the switchgear design, the inverter rating, and possible operational modes. This is a very time-consuming and extensive process involving different teams from the design and manufacturer side. The next challenge is the selection of the most advantageous star-point earthing method for the medium voltage system. This selection has an impact especially on the operational philosophy of the grid booster, namely on dealing with single phase-to-ground faults, and on the protection concept. When deciding on a neutral grounding transformer, the single phase-to-ground faults are limited to a certain level, for instance 500 amps. This allows the reliable detection and isolation of the faulty equipment. When going for isolated operation, the single phase-to-ground faults are typically of a small amplitude and are not cleared instantaneously. The faults are indicated only use dedicated metering cores and sensitive protection functions. Following the indication, the faulty feeders are disconnected after some hours by the network operator. The challenge here is to check the selectivity, robustness, reliability of the protection behavior based on transient simulations using proper inverter models. And this aspect brings me to the next challenge, namely the availability and parameterization of inverter models. When describing the requirements for energy studies and deciding on manufacturer of the equipment, it must be assured that the simulation models are available and that they are validated within the chosen software environment. This applies for both root mean square as well as electromagnetic transient simulations. These models shall provide fault right-through and other grid compliance features required by the respective standards and technical guidelines. One of the major requirements when designing a grid booster is low standby losses and low reactive power consumption. As the grid booster is operating on demand, its standby losses shall be kept as low as possible to fulfill economic and environmental requirements. The losses are checked, calculated, and measured at different stages of the project, starting at the design stage using preliminary values provided by the manufacturer, then at the engineering stage when the loss values are verified during the factory acceptance tests by the manufacturer, and last but not least, the total losses are measured on site with all components connected together. The determination of losses requires very detailed information about the battery, inverter, as well as the loads connected to the auxiliary system, and it's to be calculated on different ambient temperature levels. The difference between a typical power system calculation study and the energy studies performed for the grid booster is the number of operational points. The operational points are mainly defined for the point of common coupling on the high voltage level, for instance, different active and reactive powers at different voltage levels for short time, for example, a few seconds, and long time, for example, 1 hour operation, standby scenario, black start and self-supply operation, dynamic simulations like fault right-through and other grid compliance relevant modes. All the possible operational scenarios require good model management and often involve pre-runs in a dedicated software to check the computation time efforts. If necessary, an aggregation of the grid booster model shall be checked to reduce the computation time and so the project duration. Last but not least, using validated software models, the performance of the protection equipment is to be verified, considering different operation modes and set points of the grid booster units. The study is typically split into elaboration of a protection concept, including the determination of the set points and the software-based verification of the relay settings. Their verification is performed in an RMS and EMT software. Both of them require validated inverter models which can reproduce the short circuit current contribution of the inverter as realistically as possible. The challenge in protecting inverter-based resources is that the maximum short circuit current contribution lies almost in the same range as the maximum load current. Especially in case of unbalanced faults, there are differences to be expected between conventional, so synchronous machine-based, and inverter-based resources. Verification of the set points in an electromagnetic transient software is therefore one of the most significant milestones of a grid booster protection study. In cases where a pickup or tripping behavior of the relay is unclear, the simulation results shall be verified during hardware-based relay tests. Except from the challenges mentioned on the slide, there is a bunch of other studies required to assure proper connection and operation of the grid booster, such as harmonic, radio interference, resonance interaction, subsynchronous, torsional interaction studies. For each single step during the development, design, and engineering study, proper and stable simulation models in RMS and EMT software are of utmost importance. PTI can support you in modeling and perform all these studies to check the performance and ensure secure operation of a grid booster. That's all from my side. Thanks for your attention. I'm looking forward to your questions in the Q&A session. I'm now handing over to Marty, who will tell you more about modeling the role that BESS can play in energy systems and how your BESS project can be assessed from a system perspective.
Thank you, Rafal. My name is Marty van Blijswijk, and I'm a senior consultant at Siemens PTI. Today, I will discuss the need for flexibility in energy systems with large amounts of variable renewables. I will also go into the role that BESS can play and introduce the market modeling portfolio that we apply here at PTI to help our customers make the right decisions about BESS. Energy systems with large-scale integration of variable renewable energy sources, such as wind or solar, require flexibility from other components in the system to cope with the variability of their supply. This flexibility needs to cover fluctuations in renewable energy output over different timescales. Seconds, minutes, hours, days, weeks, seasons, and even years. Take, for example, solar PV. Clouds passing through an area on an otherwise sunny day can suddenly limit power output in a certain area, only to surge back to full capacity a few minutes later. Every night when the sun sets, power output goes to zero until the sun comes up again the next morning. This is illustrated clearly in the upper figure, which shows the availability of solar and wind in Germany over a 2-week period in the summer. But bad weather can also persist for days or weeks at a time. And even though some production from solar and wind might remain, it may be significantly lower than on a sunny day. It's also important to realize that in winter the intensity of the sun is much lower than in summer. The days are also shorter. This causes a significant variation in solar energy production over the year, as is illustrated in the bottom figure. The same goes for wind, by the way. But the effect for solar is quite significant, more significant than people might sometimes think. It can easily be a factor of 6 between summer and winter in Central Europe, and in Northern Europe it might be even higher. Even interannual variations play a role. Differences in renewable energy output can easily vary by 10, 20%, or even more than that from year to year. Countries that are largely dependent on run-of-river hydropower are already familiar with these effects. But it plays a significant role with solar and wind as well. The energy system requires flexibility to deal with all these variations. Periods with surplus renewable power availability and periods with a deficit must somehow be balanced. There are many options that can contribute to this. To name a few, conventional backup capacity, such as gas-fired power plants or pumped hydro stations, shifting existing loads to better match the renewables availability, grid capacity to balance fluctuations in solar and wind output over a larger area, where there's typically different weather conditions, heat storage, at least if the heating is provided electrically, or cold storage, such as air conditionings, other flexible new loads, such as the charging of electric vehicles or hydrogen production, which is also a potentially flexible new type of load. Curtailment is also one that I would like to add to this list. This would mean that you deliberately overbuild your renewable capacities and accept that not all of the energy produced is actually used. Doing this may sometimes also be part of the equation and be an economically attractive solution if it weighs up against the other options. One of these other options are battery storage systems. They are also part of this list, and there are for sure many more that are not listed here. Battery energy storage systems can, at least in principle, help with all of the types of variations discussed before. It can provide flexibility to the power system on all of these timescales. But BESS is not always the best option. For instance, it's not very attractive, at least economically speaking, to build a battery that only stores surplus energy from solar PV in summer and then supplies that power back to the grid during a few days in winter. In that case, you're building an expensive battery storage system that is hardly ever used. Generally speaking, you ideally want to be able to charge and then discharge a battery energy storage system as often as possible. Although it's important to keep in mind, there can also be value in having a certain quantity of energy stored at a given moment. This is, for instance, the case if reliability is a concern, or when the investment in battery capacity offsets other costs that would have been incurred otherwise instead of the BESS. A good example of this was the grid booster that was presented just before by my colleague Rafal. The main takeaway is that all storage and other flexibility options have their own characteristics, which can be advantageous or disadvantageous, but it always depends on the situation, and that's why it's important to do such analysis. It's very likely that the combination of all the options mentioned, and also some options that were not mentioned, will eventually emerge to help accommodate the variability that is inherent to renewable energy sources. Most of them at least. The contribution of each option will also no doubt change over the course of time, during an energy transition in which variable renewables are gradually added to the system. And you should keep in mind that the extent to which all these other sources of flexibility are applied will also in turn affect the market conditions in which battery energy storage systems operate. It's therefore crucial to assess what opportunities exist for BESS. This depends on a combination of the structure of the overall energy system and the characteristics of the entity building the BESS installation. For the business case, it is important to take into account future developments as well, as you want your BESS to be profitable over its entire lifetime, not only to provide value under today's market conditions, but also in 10 or 15 years from now. We at PTI can analyze the role of BESS in an energy system over a desired period of time using energy market simulation software such as Plexos. Using these energy market simulations, we can model what happens in an energy system in order to analyze the value provided by a BESS in a given time frame, or over the lifetime of a specific investment, for instance. These simulations take into account specific factors relevant to the business case at hand, and can be performed from different perspectives and for different customers. The analysis can, for instance, be done on a country level, a regional level, or from the perspective of a single prospective BESS investor. Every BESS is a component of the larger energy system. It is affected by things that happen outside of your own control, but in turn, all the BESSes together, they drive the system itself. Through energy market analysis, we can determine the optimal size of BESS for a specific client, taking into account the customer's needs in terms of, for instance, meeting a given electricity demand over time, and the conditions set by the market that it's part of. If you would like to learn more about the right financing for your battery project, stay tuned for the next webinar in this series. By combining financial expertise with specific, in-depth battery know-how, Siemens Financial Services can offer a wide range of financing solutions, long before construction starts and well into operation. For now, and also on behalf of my colleagues, I would like to thank you very much for your attention.